Okay, so that's some of the complications and fascinating facts about HQET in the perturbative sector. Let's come back and talk about power corrections. Which are, I'll go under the title of, well, maybe I should just call them power corrections. Better title. So we have an effective theory. We've so far talked about it at lowest order. We stopped at lowest order. We had this HQET Lagrangian. And we talked about using that Lagrangian to carry out some perturbative calculations. What if we went to higher order in the power counting expansion, which is 1 over MQ? Okay, so power corrections here means higher order in 1 over MQ. So let me show you how you can construct those terms. So let me go back to a representation of the full QCD Lagrangian, which we had in terms of this B field and the Q field. And when we first talked about this, we just dropped all the terms with the B. But now I'm going to do something a little more sophisticated with them and really just integrate them out. So we had this. And this was really just us writing QCD in a fancy way that was convenient for this discussion. So this is really just QCD written in a fancy way. So if we want to take this Lagrangian at tree level, we can just integrate out BV. This is a Lagrangian that has quadratic dependence on BV. So you could think that the path integral in this formula here would be a quadratic path integral, and those we can always just solve. And what effectively integrating out BV amounts to is solving for the equations of motion of BV and plugging that back in. So the type of diagrams I was drawing before where we had this wiggly line, it was a BV propagator. We can integrate out that by solving for the equation of motion. So we look for the variation with respect to BV bar and set it to 0. And that gives this equation. And we solve this formally for BV by just inverting this operator. To get that equation. And then we can plug that equation back into this equation. Which is still a QCD Lagrangian, actually. But then we expand. And once we expand, we match onto the HQET Lagrangian order by order, tree level. So the first term is the term we've been discussing. The next term, we drop the v dot d here because that's small. We just have 1 over 2 MQ. There's 2 d transverses. And there would be higher order terms as well, but we'll stop at that order. So this is L0, first order term, and this would be L1. It would be higher order terms. So what is this guy? it's useful to write that guy actually in terms of two different things, and you'll see why momentarily. So it's got two covariant derivatives, and both of them are dotted into gamma matrices. It involves this thing D transverse, which remember is the full D minus a projection onto V. So it's something that's transverse to V. So what I want to do to simplify this guy here is I want to do the following. I'm going to use the fact, I'm going to write it in terms of a field strength by using the fact that the commutator of two Ds gives me a G, and the commutator of two sigmas, I'll write, sorry, the commutator of two gammas gives me something I can call sigma. So let me write this as the symmetric piece and then the antisymmetric piece. And I do a symmetrization in both the fields and the Dirac structures. Then dt slash anti-commutator. So then since it's anti-symmetric, it automatically forces that anti-symmetric. This guy is a G mu nu. So for this piece, we just get dt squared. And this piece, once we track all the 2's, the i's, gives sigma dot g. And so the usual way of writing L1 is as follows. You say L1, using this formula, plugging it in, has two terms. And you'll see why, when I write them down, that we wanted to do this. Okay, so that's what L1 is after plugging that in. Now, the reason to do this is that if we ask about symmetry breaking, that's something that can happen from subleading terms. At lowest order, we had a symmetry, heavy quark symmetry, and that is broken by these interactions. But it's actually broken in different ways by these two terms. This term here doesn't have any spin structure, so it doesn't break the spin symmetry. It does have flavor structure because of the MQ, so it breaks the flavor symmetry. So this is a kinetic energy type correction, and it breaks flavor symmetry because of the dependence on Q in the MQ. And this guy breaks both because it has a spin structure now, and it's a magnetic moment type term. It's kind of a sigma dot B field type interaction. That's what I mean by magnetic moment type term. Okay, so that's what the subleading power corrections look like, and if we want to use the effective theory to talk about power corrections, we could do that. We're constructing them here by knowing the full theory, just integrating out explicitly the fields. Okay, which is a very nice thing if you could do it.